Thank you, Narayanan, for the introduction. And actually, there is a little bit spice of AI in this presentation. How can it help us in, bringing 3D printing to broader fields? I have, as a matter of fact, to acknowledge the great work that my PhD students, Giacomo, Andrea, and Francesco listed there, have done, and the work with my two colleagues, Professor Cremonesi and Professor Muchacha. So if you ask any of your students to go to Google Scholar or Scopus and try to combine some keywords about 3D printing and concrete, well, they come up with something blaming you because they say, we have more than 500, 600 papers per year that are published, and we cannot cope reading with that, absolutely. And as a matter of fact, if you compare the trend of the curve of the published papers on the topic with the technology uptake curve, well, where are we? Are we close to the peak of inflated expectations in 3D printing? After that, we will have a sort of disillusionment phase, or have we already passed it and we are on the industrial uptake? Well, wherever we are, it's likely that we have now in the literature and in the applications a lot of information that has to be funneled towards knowledge, and most of all towards design-oriented knowledge. And also, you go through the literature, and it's quite typical nowadays to have these conceptual maps which highlight the different topics and the different issues which come into play. As a matter of fact, in 3D concrete printing, we have to go through material design, process design, and structural design, and we have to find the effective way to combine this. Well, surely everybody knows about this. We have also listened to very, very interesting presentation about that. But the issue is that up to the fabrication of a 3D printed element, we have to cope with the pumpability issues, the extrudability, and the buildability. And a lot of effort has been done in the past years to try to correlate this conceptual performance to mechanical material indicators, mechanical material performance indicators. So, and there is quite a consensus on the fact that pumpability depends on the rheological properties of the material. Extrudability, in a sense, you can correlate to an early age tensile strength of the material to avoid the tearing off of your filament, and buildability is a development of early age shear strength, but most of all compressive strength and elastic modulus, because you have to cope with the two different mechanisms of collapse, which can be plastic or buckling. And then it comes into play the fact that, for example, when you go to rheology, 3D printing mixes are extremely stiff. So you need, if you want to make a rheological test with rheometers, you need extremely powerful rheometers. But sometimes this is a picture from an ICA rheometer we have in our lab. You need to cast liters and liters of concrete, and most of all this does not comply with the 3D printing equipment facilities. It has been quite a challenge also to test the material performance at very early ages. This is a compressive strength test done at 1 hour on a specimen, and it's something that we need. And for tensile tests, well, also some methodologies have been developed, mutuating them from self-compacting concrete technology. And we have also seen in the last presentation what is the challenge to identify an interface fracture parameter, because the material is anisotropic, and if you want to simulate the structural behavior, you need also to know how the interface behaves and which are the properties that you have to assign to them. So basically, actually, these are some of the results that we obtained in our lab with the different methodologies that I showed you before about the material thixotropy, early age, tensile and compressive strength, and the anisotropic response in the different directions. So what we try to do, the approach that we wanted to follow is, as I said, combining material, process, and structural design, and focusing at the moment on the material design and on the process design in order to integrate different variables which basically deal with the material composition and how does it affect the rheology and the mechanical properties, but how these also match with the printing parameters, because you can have nozzle geometry, nozzle shape, but also the velocity of the printing, the extrusion velocity, and also the configuration of your printing as well, in order to avoid the well-known errors or drawbacks that you can have in 3D concrete printing. And actually, what has been done so far. So most of the work, if you review it, is done on trial and error approach, which as a matter of fact is time consuming. And also, numerical simulation can help, but at the moment, we are, I would say, in an early to medium stage of development of these processes, most of all because of very high computational cost in order to model a real 3D printing and construction process, and most of all to embed into that phase changes and so on. So our idea was to do this. Okay, let's try to develop a tool which helps to control the extrusion process and to develop a 3D printable mix without going through trial and error, combining experimental tests at a reasonable scale, numerical simulation, and AI techniques. So where we started? We started with a tentative mix design and with a tentative rheology, and tried to use that as a feed back and forth for an artificial neural network. But when we went into the rheology, the issue, as I said before, was how do we measure it? Because with most of the commercially available rheometer, it's quite difficult. So we went back to the flow table test, which seemed quite reliable and effective. Also, if you want to do on a, let's say, job site in order to control the rheology of your 3D printable mixes. So we start with 3 mixes that we found in the literature, and we worked out the flow table test, identifying from the rheometer, with the rheometer, the yield, stress, and the viscosity parameters. Then in order to process back the results of the flow table test, we used 2 analytical approaches that are available in the literature and were quite popular exactly for self-compacting concrete tools. The left one is the formulation proposed by Nicolas Roussel, which works pretty well for self-consolidating concrete, and the other one has been proposed by Kurokawa. What is the difference between the 2 formulations? One, as I said, works very well for SEC, so a material which relatively low yield stress, because it's based on the fact that your cone, the truncated cone shape, converts into a flown putty completely flat. The other one works for medium to high yield stress concrete because it's based on a combined shape. There is a part which is flown and another part which remains in the form of a truncated cone. We also used some kind of digital image recognition because we took movies of the flowing putty and identified the geometry and fed it, and validated the approaches. And you can see for the 3 different mixes, the rheometer measure yielded respectively 80, 300, and 658, so it was very low, medium, and high. And you can see that the Russell formula works pretty well for the lowest yield strength concrete, works reasonably well for the medium one, but does not predict it for the high one. So likely it's a combination of the 2 approaches that we need to put into this processing of the results for the yield strength parameter. And the limits is also depends on the volume of the material that you test, because we try to apply the tests and the formulation with not the truncated cone for the mortars, but with the large slump cone for the concrete, and we found out that it actually depends on this. So we ended up with a medium size that we had in our lab, and yielded reasonably good results between the correlations. We used these rheological inputs to feed a numerical model based on continuum fluid mechanics that we have developed in our lab in order to simulate the 3D printing process. As a matter of fact, is the last one on the right by Giacomo Rizzieri, who is quite finishing his PhD thesis now on these topics. Works at the scale of the filaments. We are able to simulate the printing process, and as a matter of fact, is based into the Navier-Stokes equation with the balance of linear momentum and balance of mass, and we implemented into this Bingham fluid, so it's rigid plastic, if you will say. We are now going to implement rigid viscoplastic. We are now going to implement also elastoviscoplasticity into that. It's based on the particle finite element model. You see there we start from a set of points and we generate a mesh, and through the Delaunay triangulation process. After that, we have to implement some element distortion control technique, which does not only work to take out the elements which at the beginning of the tool of the problem modeling are too distorted, but also helps us in keeping the computational time reasonable and removing elements which become too much distorted into the process of deformation. We calibrated and validated with some own results and some literature. You can see here some printing processes varying the print velocity, varying the yield stress, and you can see also that if you print too close, for example, to the surface, you have a flattening of the filament deposition, and the comparison between the modeled and the predicted result is here. So this was the first part of the work. Then we wanted to feed to to help with an artificial neural network tool, because we said, okay, these are mixed from the literatures, but what if we want to design our own mix with our own constituents and so on? So first of all, we had to build up our tool and identifying which are the relevant input and output parameters. So through a simple literature analysis and frequency of the records, we ended up with the list of inputs, which is there. Basically, they are mixed design parameters. Well, this is quite a hard task because in the majority of the papers on 3D printing, the information on the mixed design is obscure, foggy, given in strange proportion ratios, and because of industrial protection reasons and so on. And as a matter of fact, this makes difficult to have a consistent set of data that you need to feed data analysis tool. We wanted in the beginning to end up with a double output network for both yield stress and viscosity, but then viscosity is not much as important for the 3D printing process. On the other hand, if the yield stress is not always present in all the papers, the viscosity is even less present, so in that case it was even more difficult. The other thing was important for 3D printing, which is the time frame over which the yield stress parameter has been measured and where this time frame starts. From the contact of water with the powders is what we agreed upon. But we found, for example, going through the papers that contained this information, that about 70% of the data had a record which was in the first 40 minutes, which we deemed as reasonable for a 3D printing application. But this shows you that, for example, starting already from a broad surveyed literature which yielded us only 485 records in terms of information on the mixes, if you have to go down and clean up from what you really need and you have all the complete information, you go down to 304 measurements for which you have the complete information also about the time at which was measured. And most of the measurements, as is shown there in the cake diagram, is done on rheometer, so it was okay for us. Well, these are just the results for the calibration of the neural network and the validation of the error. We use the usual tools for calibration, feeding, and training. But what was quite interesting is that in the end, we tried to design 5 mixes completely from AI, basically, and we obtained reasonably good prediction. Just in one case or 2 cases there was fairly high. There is also the problem with that with such a low amount of data, you can risk in some cases the overfitting of the network because it has learned from itself to be too good in making this performance. But in the end, among these 5 mixes, we selected one that was able to fulfill the predictions that we have both from the literature and the AI worked fairly well in giving us mixes, which behaved well there, but also which was behaving well in the first small-scale printing process that we did. And as you can see, well, you can claim if you did everything with AI, why you have so many people there happy about the results. But this was, the students who collaborated in developing all the different parts of this work in which we combined experiments, artificial neural network analysis, and the modeling for the 3D printing. So coming up to the conclusions, I think that we are just in time. In this study, as a matter of fact, we have provided a contribution integrating experimental testing, trying to identify also a test which could be good for field measurements of the rheological properties of a 3D printing mix, and have combined it with an artificial neural network simple model which helped us in designing the composition of a mix with the required rheology, which proved fairly well from the test, from the flow table test. Also, we pre-designed with a computational fluid dynamics modeling tool our 3D printing process, and results also of the modeling, which was calibrated on the literature, was fairly respected on the first experimental trial test that we did. As a matter of fact, everything is quite promising, looks very promising, but surely we need further refinement and also enlarging the database, and also as a community to agree on the ontology of the data that we need in order to make all the research and knowledge that we are developing useful for developing design-oriented tools. Thank once again my co-workers, the funding agency, and you all for your attention.